All right. Good morning, everybody. Today we're going to be doing 2016 numbers 1 and 2. Um, and it's starting to seem hopefully kind of familiar, these types of problems that are coming up. They're very repetitive and just different types of questions they can ask for each. So let's jump into number 1 for 2016. This is Calc Active, and it looks like a chart problem, which we've seen a number of these. It says that water is pumped into a tank. So we got into a tank, which means rate in. Okay, we got a rate in modeled by this equation here. Liters per hour for 0 to 8, where T is measured in hours. Water is removed, okay, so that's rate out from the tank at a rate modeled by R of T, which is given in the chart. Liters per hour, where R is differentiable, which implies continuous. Okay, and decreasing on 0 to 8. So, and it says it's decreasing. Okay, on 0 to 8, and selected values of R of T are shown in the table above. At time equals 0, there are 50,000 liters of water in the tank. All right, we got a lot going on here. We got a rate in with an equation. We got a rate out with a chart. We got initial amounts 50,000. Let's just kind of use all the information, keep all that in the back of our mind. Part A says estimate R prime of 2. All right, well, so we're given R right here. R prime, since R is already a rate, R prime would be the rate of the rate, which is acceleration. So it wants us to estimate the acceleration at time equals 2 and show the work that leads to your answer. Well, we're just using the chart for that. So 2 is right here between 1 and 3. So we've done this countless times. This is going to be, so R prime of 2 is approximately going to be equal to R of 3 minus R of 2, or R of 1, I apologize, over 3 minus 1, which is 950 minus 1190 over 3 minus 1, which comes out to be negative 120. This is acceleration, so it's going to be liters per minute, no, per hour squared. Okay. So there you have it. Average rate of change of my rate of change. Cool. Let's go on to B. B says, all right, so we got a chart. B says to use left Riemann sum with 4 subintervals. So there's 1, there's 2, 3, 4. It says to use left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed, because remember this chart here is my rate out from the tank during the 8 hours. And we want to also classify if it's an overestimate or an underestimate of the total amount of water removed and give a reason why. Okay, so remember left Riemann sums, we're going to start with the leftmost value, and we're going to have 4 rectangles, so 4 products here. So we're going to say that the, because what we're estimating is the integral 0 to 8 of R of T. That's what a left Riemann sum does. And that approximation is approximately equal to, so the first rectangle has a length of 1, 0 to 1 is 1, times the leftmost value, 1340, plus 1 to 3 is 2, times the leftmost value, 1190, plus 3 to 6 is 3 times 950, and then plus 2 is 6 to 8 times 740. All right. So there's your left Riemann sum. Again, we used these values here, and it's Calc active, so you should be able to, go ahead and just type that all in your calculator and actually get the answer. And it ends up being 8,050 liters. 8,050 liters. Now it also wants us to indicate if this is an over approximation or an under approximation. Okay. Well, think about it. This function, like if I map this out 0, 1, 2, or we'll say 3, 6, and 8. If I were to plot these points, it goes boom, 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 something like that. Okay. It says in the problem that it's a decreasing function, which means if I were to draw this out, it looks something like this. It's a decreasing function. So remember what left Riemann sum does with decreasing functions. Remember, if I start off at 0 here, if I start off at 0 right here, what does a left Riemann sum do? It's a over approximation. You can even tell that. That's just definition. So we're going to say that this is an overestimate. So over. And the reason is just that. Left Riemann is an over approximation for decreasing functions. All right, so there you go. We got the approximation, and then that it's an over because it is just the definition of left Riemann sum for decreasing functions. Cool. All right, part C. Part C says use your answer from part B, which we got 8,050, to find an estimate of the total amount of water. Okay. Total amount of water in the tank to the nearest liter at the end of the 8 hours. So remember, we have a rate in, rate out problem with an initial amount of liters. So if I want to know the total amount, we're going to set it up exactly like we always do. All right. Remember the formula for total amount of water in a rate in, rate out problem. It's initial. It's the initial value plus integration 0 to 8 in this case of rate in minus rate out. Okay. It's just that we don't have an equation for the rate out. It's just in the last problem we estimated what rate out was. The rate out's accumulation was 8,050. So how we're going to set this up, total amount, there's no E in amount, all right, is equal to the initial amount of water in my tank, which is 50,000, plus the integral of the rate in minus the rate out. The integral of the rate in is 0 to 8 of my rate in function, which is W of t dt, given right here. Okay. And then minus the integration of my rate out, which I estimated in part B. So we're going to say minus the amount coming out, which was 8050. And that's it. So Calc active, so you can do this in my calculator, and I went ahead and stored this in my y1. So I just did the integral of 0 to 8 of y1 in my calculator. And it was 50,000 plus that integral ended up being 7836.195325 minus 8050. And then combining those three numbers together, you get approximately 49,786 liters. Because it did want you to round to the nearest liter. So that's the nearest liter. All right. Not too bad once you know what it's asking. Total amount is initial plus integration of rate in minus rate out. All right. And then lastly, D. D says, for 0 to 8, is there a time? So we're trying to prove that there is a time when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank, and explain why or why not. Now the thing is if we had two equations for the rates, we just set them equal to each other and solve. But for one of them, we're given a chart, we're given a snapshot. So we're going to have to prove using some theorem that this is going to be the case. So essentially what we're trying to prove based off of this problem is we're trying to figure out, is on this interval 0 to 8, is there a time on 0 to 8 where R of t well, yeah, let's say R of t, sorry. R of t equals W of t. Okay, is the rate out equivalent to the rate in? Okay, so that's what we're trying to figure out. So we got to think about some theorem that we can do to make this work. Now, so we're talking about the rate at which the water is pumped into the water, and the two equations are talking about the rate at which the water is being pumped in or being pumped out. Okay, so we're trying to figure out if there's some value on my function. So it's trying to figure out some value. It's trying to say, like, all right, is there a value over this interval? Which is not going to be mean value theorem or Rolle's theorem, because those are talking about the rates of the functions given. All right, here it's asking about the rate of the water pumped into the tank and the rate pumped out. Well, those are values of my function, so I'm specifically talking about a value of a defined function, which that's going to have to be intermediate value theorem. So because we're talking about two functions though here, and we're trying to decide this right here, this is another way of saying, is there a point where R of t, well, I guess a better way of saying that is my rate in minus my rate out. So my rate in is W of t. So I'm going to say, is this W of t minus R of t equals 0? That's weird. So I'm trying to figure out if from this, is this true? Okay. Well, intermediate value theorem is saying, okay, let's look at the endpoints, okay, and see if the endpoints are on either side of this value 0. And we also got to discuss that it's continuous for both functions. And it says that the chart is differentiable, so therefore it's continuous, and this exponential is continuous over the interval 0 to 8. So that part's a check. So first of all, let's figure out, okay, what is W of 0 minus R of 0? Okay, which if you do W of 0 in the calculator, you're going to get, like if I plug 0 in for t into this equation right here, you get 2,000. And R of 0 comes from the chart, that's 1340. And that's equal to, well, it's a positive number. It's equal to some numbers. See, it's going to be what? 660, which is greater than 0. Okay. Well, what about if I do the other endpoint, W of 8 minus R of 8? Okay. If I do W8 in the calculator, you get 81.524. And R of 8 from the chart is 700. Now, I didn't figure out what that difference is, but it is definitely going to be negative, which is less than 0. Okay. All right, so think about it. There has to be some t value between 0 and 8 that the difference is going to have to equal 0, which is another way of saying that the rates are equal to each other. And that's based off of intermediate value theorem. So I'm going to say, I'm going to kind of state this out a little bit because we kind of showed all the criteria. I'm going to say a since then statement here. I'm going to say since, let's say the continuous part first. Since W of t minus R of t is a continuous function. And I should probably go into a little bit more detail than that. WT is continuous because it's this exponential, so it's continuous on its domain. And R of t is continuous because it says it's differentiable, which implies continuity. So both pieces then would be make it a continuous function. So since it's continuous, and W0 minus R0 is, well, I should say that the other way around because W8 is the smaller function. So I'm going to say W8 minus R of 8 is less than 0, which is less than W of 0 minus R of 0. Okay. So because there's that interval is true, then by IVT there must exist a number t on the interval 0 to 8 such that the difference w of t minus r of t equals 0, or another way of saying that is w of t equals r of t, okay, which is what I'm looking for. So that was kind of a stretch, I know, but the idea was to first recognize that they are asking about a value, all right, of a function, and so that's IVT, a value over an interval, okay, where we have two endpoints, so not a rate of change, so it's not going to be mean value theorem or Rolle's theorem. And since we're talking about two functions, we had to discuss it as w of t minus r of t. So I looked at one endpoint with 0, one endpoint with 8, and I discussed the continuity. So then we just did the criteria, all right, the criteria for mean value theorem, or I'm sorry, intermediate value theorem. Then we did our then statement and stated the conclusion that there's got to be some number t on the interval 0 to 8 such that the difference is equal to 0, or w of t equals r of t. So that was a little bit more fun of a problem, but anyway. Here's the answer key. So part A, we got the estimate, and we got the units. We did the left Riemann sum, and we got the estimate to be 80/50, and we got the overestimate with the reason. It just pretty much states that it's an overestimate. C, we got the correct integral set up, so our three values there, and we got our estimate. D, we considered the fact that we're doing w of t minus r of t, and answer with explanation. So we only got 2 points for D, even though we had a lot of conceptual knowledge there. But I would assume that for answer with explanation, you got to have intermediate value theorem thrown in there somewhere. So they might have been a little lenient on that. But there you have it. That was number 1. Let's move on to number 2. Number 2 is not so bad. I like number 2. Number 2 says, at time t, the position of a particle moving in the xy plane is given by the parametric function, okay, the parametric functions x of t and y of t, okay, where the derivative of x is given. Okay, the derivative of x is given, the rate of change of x, and the graph of y consisting of 3 line segments is shown in the figure above. So it's interesting in this problem. I think this is an interesting problem. They tell you the derivative of x, but they tell you the position of y. So they're giving you two different things here. They're giving you the derivative for x, but they're giving you the position for y, which is interesting. Okay. So it says at time equals 0, 2, we have an initial position of 5, 1. I'm going to use this knowledge to find the position of the particle at time equals 3. Okay, so let's do it for x. We got to do it for x and y. So let's do it for x first. Okay. For x, let's say x of 3. So let's figure out what x of 3 is. So with x, we're going to start with our initial point, which is at 5. We're given that it's 5. So I'm going to do 5 plus, and then the change in x from time equals 0 to time equals 3. So I'm going to say the integral 0 to 3. That's ugly. Can't read that. Integral, why is it doing that? It's very, very frustrating. Oh my god. Alright. Well, give it a second. It's going to have to, that's not good. Please, come on. Dang it. Why does it do that? Alright, well. Picked it up, I guess. I was about to be very upset if it deleted all that. Alright. Oh my gosh. Okay, so x of 3 is going to be my initial value 5 plus the integral integral 0 to 3, okay, of my rate of change for x. So t squared plus sine of 3t squared dt. All right, which if you do this out in the calculator, you get 5 plus 9.3770358089, or just simply 14.377. Okay. So we started off with the initial x value, we added the accumulation of distance of x. Now y of 3, well, we're given the position for y as a chart. So y of 3, so at time equals 3, my y position is at -1/2. So that's nice. They went ahead and told you the position there in the chart. So my point is at 14.377, comma -1/2. Not too bad. All right, B says, find the slope of the line tangent to the path of the particle at time equals 3. We've been asked that question numerous times in numerous settings because it's saying, the slope of the line tangent at time equals 3. All that's asking for is dy over dx at the point time equals 3. That's it. That is the slope of the tangent line, time equals 3. So all we have to do is have the derivative of y over the derivative of x at time equals 3. Okay. So the derivative of y, so I'll write it out this way. This is the same thing as saying y prime of 3 over x prime of 3. That's the same thing. Okay. Well, y prime of 3, see, remember the graph is the position of y. So at 3 here, I'm looking for the slope at 3. What is the slope of this line right here? That's going to be equivalent to 1/2. So y prime of 3 is equal to 1/2. It's just the slope of my position function. And x prime of 3 is the derivative of is just plugging 3 into that function right there. It's giving me the rate of change. All I did there was 3 squared plus sine of 3 times 3 squared. That's all we have to do there. And in my calculator, if I do that out, I get the final answer of 0.0502190761, or just 0.05. Okay. So there you go. That wasn't too bad. Let's go on to C. C says find the speed of the particle at time equals 3. All right, well, we've done speed a bunch of times too. We know that speed is equivalent to the magnitude of velocity. And the magnitude of velocity is the square root of, okay, we're doing it at time equals 3. So that's going to be x prime of 3 squared plus y prime of 3 squared. Okay. Which again, I did that. We got those values in the previous problem. Like you got this value in the previous problem and this value in the previous problem. Like y prime of 3 was 1/2. And I didn't tell you what x prime of 3 was, but if you plug that in for t into the dx over dt equation, it was like 9.956. Dot dot dot. Well, anyway, if you do those quantities squared and take the square root and all that stuff, you get the final answer of 9.969. Okay, so, C was just a formula, so you just had to know speed, and that's it. Okay. And then lastly, D is honestly it's just a formula as well, but it's a little bit tricky of a problem. Okay, so total distance, remember, is the integral. Is the integral of 0 to 2. Okay, integral 0 to 2 of the magnitude of velocity or speed. Okay, which we wrote that out in part C. It's going to be the integral 0 to 2 of the square root of x prime of t squared minus y prime of t squared. Okay. Here's the interesting part. Like x prime of t, I have an equation. I can just plug in. I can plug in this right here. That's fine. But y prime of t, I don't have an equation for. So what do I plug in for y prime of t when I'm doing the integral on my calculator? Okay. Well, remember that y prime of t is just the derivative of t from 0 to 2. So if I look at my graph up here, here's 0, here's 2. I may not have a function. I may not have a function for 0 to 2 here, just 2 line segments, but I do have only 2 derivatives. From 0 to 1, the derivative is negative, it's a negative 2. And from 1 to 2, the derivative is 0. So I don't need a function for y prime of t because I know it's only going to be 2 values. So why don't I just break up the integral over those 2 values and plug in the derivative? Let me show you what I mean. So this is, I'm going to write it up here. This is what the equation needs to be. You need to split it from 0 to 1, okay, of the square root of, and then my x prime of t squared, okay, because that's just a function. And I said minus here, I don't know why I was going to say plus. And then plus y prime of t. All right, so from 0 to 1, y prime of t is just going to be negative 2. All right, it's a constant value. And then I can add that to the integral, and I'll do it right here, integral 1 to 2 of the square root of x prime of t squared. And then my derivative from 1 to 2, my y prime of t over that integral is just 0 squared. So it's not the fact that we could just plug in an equation for y of t. We had to just put in a number because it's 2 line segments. And so we had to do 2 separate intervals. Okay? But x prime of t, we could just leave the function in. All right, so if you do each of those, so like the integral 0 to 1, I got to be 2.1237871,232, and I added it to the second integral, which I got to be 2.1120025513, and that adds up to 4.350. Okay, so that's your total distance from 0 to 2. That was an interesting one. I think that was pretty interesting. So we went to here and then down. All right, good stuff. All right, well, here's the answer key. So we set up the correct integral for part A to get 14.377. We used the initial condition of 5 to get that answer. And when our answer was 14.377 and negative 1/2. Okay. B, we got the correct slope. We set up the correct formula here. C, we did the expression for speed that we've known forever and got the answer. And then for D, it was worth 3 points. We set up the correct expression for distance. So if you were lost after this point, that's fine. You still got a point for just knowing the expression for distance. So that's why I think it's always helpful at the beginning of the problem, write down the definition you need to know for that equation and then start trying to plug in stuff. The different integrals with the different y of t values, and then the answer. Okay. All right, cool. So that was questions 1 and 2 for 2016, and we're going to do 3 and 4 here in a bit. So, good job, guys.